All right, and with that, I think we can actually also get started. And it is my great pleasure to welcome Gaël. Gaël is a research director at INRIA, but he's probably most well known as a co-founder of scikit-learn. And I'm pretty sure like all of you have either used scikit-learn or actually have a co-worker or a student using scikit-learn. So really impactful software. And he's also co-founder of Probable, which is, correct me if I'm wrong, company that is around scikit-learn to actually sustain the development of scikit-learn. And today we're going to learn more about how scikit-learn and the new library called skrub can actually help us pre-processing data modality that we heard quite a bit about already, namely tabular data, and can help us pre-processing that in a more automatic fashion. And with that, please join me in welcoming Gaël.
Thank you. Thank you very much. All right. So indeed, I'll be talking about pre-processing tables and scikit-learn and skrub and other things. So maybe I should first define a bit what kind of tables I'm interested in. So typically, I mean, with scikit-learn, I worked with many application domains, but industry, banks, and insurances. My personal interests are in healthcare. Anyhow, the kind of data I typically have looks like this. So what do we have? Well, we have categorical data. We have columns of different nature, different distributions. We have missing values. So, this is not your typical bunch of numbers. And so typically, when our machine learning models are adapted to a bunch of numbers. And so typically data preparation means that we take this data and we adapt it to our models. And this means making it regular enough, with quotes, for the model. And those transformations are typically not automated by traditional machine learning. And so as a consequence, or maybe not as a consequence, but in practice, if you do industry surveys, people report that the #1 challenge to data science or machine learning in the industry is quote unquote dirty data. Of course, what does that mean? It means many, many things. But my experience is that it partly means this adaptation. So in practice, what you find when you talk to people is that most of data science is actually data wrangling, so basically transforming this data, typically using pandas or SQL. And my agenda is that better pipelines can reduce this needs. So I'll be talking a bit about this. Of course, there are many problems we will not solve. And we could have a discussion about, can we go further or can we not go further? So this is a tutorial. So we're going to do a bit of hands-on, just to show you that get you started. And we're going to start with skrub. And the table that I presented earlier can be downloaded with skrub. So skrub, just like scikit-learn, has a datasets module, which, just like scikit-learn, you need to import, right? It's not directly imported with skrub. And then you can fetch this table, which we call the employee salary. I'm sorry, I think it comes from the Texas Employee Registry, but yes, I think it does. Anyhow, and we take a proxy problem, which is predicting the salary. It's not meaningless, by the way. And so, we have X and Y, where X here is a data frame. It's a pandas data frame. And so I'll get us started with a bit of hands-on. I want to start with the hands-on and then describe a bit what goes behind. And I'd like you to try to use the tabular learner function of skrub to get a predictor that can work on the data frame. And then you can, for instance, use cross-val score to see how well it performs. So, I gave this assignment, the tutorial I gave earlier a few months ago, and the first difficulty was installing skrub. So you should be able to pip install it or conda install it. You can do this on a Google Colab if you want. You can do this on your own computer if you want. And the second difficulty was importing datasets. And so you need to do from skrub import datasets. It's not imported with skrub. Okay. And if, by the way, if you done early, because this is actually only a few lines of code, you can even play a bit with what you got, what model, try to figure out what's this model. And play a bit with Scrub. There's a getting started page. So when someone has a prediction, can that person raise their hand? Also, if people are stuck, they can raise their hand and I'll come along. Okay, so I don't know if people had managed to get predictions. I moved forward a bit. So really, it was just a question of importing the right imports. I called the data frame DF. I like to call my data frames DF. And I used scrub.tabular-learner quote regressor to get a model, specifically a regressor. This is why I need a quote regressor. I could be getting a classifier. And then I use standard scikit-learn tools, for instance, cross-val score, to get the prediction accuracy cross-validated of this regressor. So what's interesting and what's different from your typical scikit-learn usage is that we're applying this directly to a data frame. And that data frame, if we look at it, is slightly complex. So a Scrub has the table report object that can help you have an idea at what's in a data frame, and we can see that they're all kind of different columns in the data frame. We have things like dates, things like strings, things that look more like categories, numbers also. Just to give an idea of the kind of things a Scrub can do, you can click on the different values and get an idea of the data type, of the distribution of values. Here we have the distribution of your first hired. We can see this distribution probably tells us that the data set was stopped in 2016 because the highest value is 2016. We also have a tab that tells us about column similarities, and here it has a warning sign. The warning signs come from the fact that two columns are extremely strongly associated, department and the department name. And if we look a bit more in details, what we'll find is that department and department name are actually they convey the same information. There's a one-to-one mapping between those two. So this is computed using the Cramer V statistic. So that table report is another example of the things that Scrub do for you. So basically, you can now see the mission of Scrub. We're trying to make a learning or data science on tables as easy as possible. Okay, and there's more in Scrub, and I'll cover more in Scrub. Scrub is a fairly young package, and we're trying to rather focus on the quality of features rather than the quantity of features. So any questions at this stage? Well, the obvious question is, how does tabular learner work? So this I'll cover it, and that's kind of the rest of my presentation. Why does table report not take the Y values? Well, because the notion of Y value is very associated to machine learning, and that's actually a challenge. So scikit-learn took a problem that's easy to formalize. It's learn the conditional distribution of Y given X, or predict Y given X. Data science is often more complex than this, and in Scrub, as we go, we want to extend it to beyond this very closed problem set. And it's actually harder from an API perspective because you get into very open thing. So you have pandas or SQL that are completely open and you can do whatever you want. You have a scikit-learn or machine learning toolkits that are completely closed. I have X and Y and this is closed, and we're trying to figure out a bridge between the two. So that's why. Any other questions? Okay, so I'll switch back to presentation mode. So really, the code was this, right? It was a few lines of code. I'll switch back to presentation mode, and depending. So, do you want this to be more slide mode thing where I talk about both theory and empirical results we have, or do you want this to be more interactive? Oh, okay, so we have interactive. All right. So I'll have to switch back to slides, to notebooks then. Okay. All right. So, and my slides are broken. So I'll be talking about a few things. I'll first be talking about like a more traditional machine learning problem, which is machine learning has, at least for tables, has really focused on numbers. So I'll first cover, what do we know in terms of fitting numbers. More traditional kind of stuff, but giving some understanding here. Then I'll cover how do we encode messy tables. We go from the tables I've shown to numbers, and then I'll cover end-to-end, putting things together, including with a neural network twist. Okay, so let me start with fitting numbers, basically. So if we roll back a few years ago, and I know that thing got vastly cited. We actually the story by the way. So this is a paper that basically showed that on typical tabular data, deep learning doesn't work that well. And Leo is maybe in the audience, maybe not. The story behind this paper is not that we wanted to show this. The story behind this paper is that we were trying deep learning, including the latest, greatest methods. And we were frustrated at the fact that we couldn't really reproduce the successes. And eventually we made an analysis behind this. Okay. So really the thing is that deep learning struggles, whereas tree-based methods have it really easy. Even if you look at tables that are only made of numbers, you throw away the categorical columns. And so one question is why? And so this is true, by the way, for regression and for classification. And so one question is why. And so we haven't updated, this study with the latest method, and new things have happened. Of course, this was a few years ago. But really, the question is why. And the reason is the kind of data we're looking at has typically various marginals that are different and non-Gaussians. And so you might have different marginal for each feature. Each feature is meaningful by itself. Typically, you might have the age, I might have the height, and it typically has many categorical features. Okay? This maps really well to the inductive biases of trees. Trees, if you picture how a tree is built, a tree first, iteratively selects one feature, then selects a cut on the feature. Selects another feature, selects a cut on the feature. So the tree is intrinsically, focusing on those columns individually. If you think about a linear model or the first layer of your typical neural network, the first thing it does is a linear combination of all the columns. The kind of inductive bias is extremely different. One is, centered on the column by itself. The other one is centered on a linear combination of the column. A linear combination of the column doesn't always really make sense from an application perspective. I'm going to do 0.1 times the height plus 3 times the weight. I was trained as a physicist. I'm like, God, the units don't match. So the trees are terribly naturally aligned to the kind of features of tabular data. Now, of course, we need to define what tabular data means. If the tabular data is actually a set of a dozen sensors all measuring temperature in an industrial device, then maybe it's a completely different thing. And maybe, the kind of linear combination that you have actually means something. It's like, interpolating between the sensors. But the typical tabular data that I see is more made of columns that have different meaning. And then something that actually surprised me is that what we find is that we found that in many of the data sets that we looked, the regression function, so the function that links y to x, actually had some very non-smooth behavior. So for instance, electricity consumption jumping at some stages of the day. And so non-smooth behavior is typically very hard to learn in general, but tree-based methods do that. Okay, so the problem space we're in is a problem space that's difficult for deep learning, because deep learning, when you think about it, is fundamentally based on smooth optimization in vector spaces. Fundamentally, all this, the vector space is equipped with a metric that's typically the Euclidean metric. If you do a gradient step, you're in a Euclidean space. All this is invariant by rotation. It's not axis aligned. All this is notions of distances that may not be meaningful if you have jumps in your data, if you have categorical values. So it's really a difficult space for deep learning. All right, so you can do things to improve deep learning. So in Leo Greenstein's work, we used scikit-learn quantile transformer. So the quantile transformer is something that basically matches the quantile to make the distribution of the different features more regular. So David, who's David Holtzmiller, who's sitting right here, has a very interesting paper with Leo, actually, not with me. I didn't bias that paper, not too much, where he uses an interesting combination of a robust scalar. So robust scalar is basically, the standard scalar in scikit-learn, but it's robust to outliers with tail squashing nonlinearities to transform the input distributions into more regular distributions. So you have to keep in mind that those input distributions are going to widely vary. You're going to have things like income distributions. Unfortunately, income distribution has very, very long tails. Some people made a bucket load of money, and that's true of many things. You have very nonlinear and non-regular distributions. So some of the things that help neural networks is to make everything more regular, closer to Gaussian. And I'll come back to neural networks, and I won't cover all the work of neural network. I won't cover, for instance, the work of TAP-PFN, because France would explain this, or many other people would explain this much better than me in the audience. But first, I'll cover much more preprocessing. And let me talk a bit about missing data. I was quite happy to hear in Rich Caruana's talk this morning reference to missing data. So missing values are very frequent in applications I'm interested in, which are health and social sciences. From a purely formal perspective, the reason your goddamn machine learning doesn't work on missing values is that, once again, the missing value doesn't sit in vector space, and I can't just compute my gradient or you name it on it. So it's, you can fix it, but you can't just, take your standard algorithm and throw it there. So the standard approach is imputation. And here I'd like to stress that We want imputation that can be applied out of sample. By this, I mean we want an imputation that we can train given data and apply given new data. So if you know scikit-learn well, it's an imputation that can do fit and transform. Okay. Imputation is typically understood as filling in the blanks with likely values. Okay. So once again, I really want to stress that we want to separate training and applying imputation. First of all, if you don't do this, you can't even put your model in production, because if new data comes in and you need to refit an imputer, that model is going to cost bucket loads of money. And second, imputing the full data set, the train and the test jointly can create leaks. The reason I'm stressing this is that a significant fraction of the benchmarks on imputation methods don't do that. Why don't they do that? Because, if you do your imputation inside your cross-validation loop, it's much more expensive. So people don't want to do that. I consider those benchmarks as invalid. They can't conclude from them. Okay. So back to imputation, the simplest imputer that can work separating, training and applying the imputation is the mean imputation. So it's a special case of univariate imputation. So you learn the mean on the train set, and then you replace all the missing values by the mean. This can be done in scikit-learn by the simple imputer. And if you take your classical textbook statistic point of view, you shouldn't do that. It's disastrous. Why is this disastrous? It's disastrous because it distorts the distribution. So here I'm showing you the mean imputed data, and it's like in Rich Caruana's talk, you can clearly see where the value has been imputed. So you've created a distribution that doesn't match the underlying distribution. If we want to go further, the kind of statistical results that are behind this is that you need what's known as congeniality conditions. So the imputation must preserve the data properties that are used by the later analysis step. So for instance, if I use a linear model with a L2 loss and an L2 penalty, right, basically, then I'm only, the Gaussian statistics are sufficient statistics of the problems, so I only need to preserve Gaussian statistics, so I only need to preserve the mean and the standard deviation of the data, or the mean and the covariance. Okay, so you can immediately see that if we go back to those are classical statistical results. If you go back to classic statistical result, there's in the results for imputation to work, and I'll define what works means. There is this notion of matching between the imputation and the analysis model that's behind this. And so typically, what people do is conditional imputation, which is that you model one feature as a function of others, and then you use all kind of models. And one possible way of doing this is to iteratively predict one feature as a function of others. And in scikit-learn, this is done in the iterative imputer. Now, I immediately want to stress that the computational scalability of this thing is disastrous. So, you take your base learner, the one that you give to your iterative imputer, and you need to fit it several times. You need to fit it multiple times, where multiple times is the number of features you have. So if if n is large, or p is large, or any of the two is large, it gets absolutely disastrous. Typically you're many times more costly than your base learner. Plus, stopping criterion on these things is kind of hard, and in scikit-learn, we don't really know when to stop, right? Okay, and in benchmarks, typically that's a big problem. Okay, so I'm not going to go too much in the statistics, the statistical results behind imputation, but I still think that it's very important to take a statistical point of view on the different things that we do. And there is there is a well-developed theory behind missing value in statistics, where the question people have been asking for the last 50 years is, can I fit a parametric model on data with missing value and have parameters of my parametric model that are the same than the parameters I would have if I had observed the full data set? Okay. And so there's a lot that has been done there. I think we shouldn't ignore it, and I'll cover it briefly. I want to stress that the question we're asking is a different question typically. It's, can I use a non-parametric model to predict as well as possible left out data? And there's a difference between the two. I'll come back to this. Okay, so central results of missing value theory lead us to differentiating different scenario in missingness. The one for which it's possible to derive strong statistical results is known as missing at random. And a missing at random scenario is a scenario where an entry, whether an entry is observed or not, is independent of the value of the entry, conditionally on the others. Okay? So this is a missing at random setting. So typically, if I have a setting where the value, whether a value is missing or not depends on the entry, I'm typically not in an R setting. So for instance, when I have censoring. So if we go back to the example of Rich this morning, Rich had an example, I don't remember what the value was, but basically it was missing more often for very large values, okay? This is a missing not at random setting, okay? You're missing more often for very large values. So in missing not at random setting, the missingness is said to be non-ignorable. And you can only get statistical results by modeling the mechanism. The important point is that without going into too much of the theory, the MAR assumption grants the validity of the common statistical procedures, such as expectation maximization, which was actually invented for missing value, or imputation plus just using a model on the imputed data. I'll say this once again. There is no statistical reason that if you're not in MAR, imputation will lead you to good statistical object. Okay? That's very, very, very important. Okay. Now, switching to predictive settings. In predictive settings, a few years ago with Marine Lemorvan, who's been really leading this research in my group, so we derived a very strong theorem, and I'm not going to go into the formal writing of the theorem, but considering a prediction setting, on which we use a universally consistent learner. What's a universally consistent learner? A learner that can approximate any function. Then this will lead to optimal prediction, whatever the missing data mechanism. So we don't need the MAR assumption, and for almost all imputation function. Okay, so it tells us that asymptotically, with a very flexible learner, you don't need to impute well to predict well. What's going behind this is that the flexible learner will just recognize the imputation, because imputation creates patterns in the data. It will recognize the imputation and will use this to predict. Okay, the difference between this result and the statistical result that I was showing before is that before, those statistical results were A, using parametric models. We're not using a parametric model here. We're using a flexible model. B, striving not to predict well, but to recover the same model parameters than on fully observed data. Okay, so basically, I don't need good imputation. I can just impute whatever. But that's an asymptotic result. In practice, you know, can some imputation help my learner? So here are a few simulations, and we'll do a bit of hands-on on this. So here I'm using a missing completely at random. So missing completely at random is the simplest kind of missing value setting. You know, the missingness is completely independent of the data. It never happens in real life, by the way. and gradient boosting. And I'm showing, learning curves. So as a function of the amount of data, I'm comparing mean imputation with iterative imputation. And what I can see here is that with a small data, iterative imputation actually helps. Okay, so maybe I should be using iterative imputation, even though it's very costly. Well, in no way can it be enough. So when I have predictive missingness, and the brutal case is when the y that I'm trying to predict depends only on whether the data is missing. And for instance, it could be happening in fraud detection. I'm in a NAR setting. And then imputation makes prediction impossible. Because if I've imputed perfectly, I can't predict. Okay, so there's a simple trick, and that's really important. It's just you add a column that tells you whether you've imputed or not for each feature where you're imputing values. In scikit-learn, that's done with adding indicator, okay? And so if we go back to my simple simulations, here now that I'm adding the indicator, what I can see is that the convergence happens much, much faster, and basically mean imputation actually performs better than iterative imputation. Now, this is using a gradient boosted model. Gradient boosted models are very good with brutal irregularities. So gradient boosted models, or tree-based models, are going to be very good at modeling this irregularity that we've created. This may not work for everything. So we said we would do a bit of hands-on. So you can go to this URL. I'll do it with you. And we should have a way of starting. So we'll do the missing value, machine learning with missing values. And you can try both of these. You can either try to launch Binder. Binder is an online. You can also download the notebook, by the way. Launch Binder, or try to run it locally in your browser using Jupyter Lite. And let's see if this launches. We can also download it if it doesn't work online. Sorry. It's dirtydata.science/Python. This is a very, very simple example that hopefully will help you build up a bit your intuitions. Okay, maybe the binder is going to take forever to start, and maybe I'll download the notebook. So I've downloaded it. And so what we're going to do here is we're just going to do very simple simulations. This, it could be a simpler simulation. I'm just simulating two features, x1 and x2, or x0 and x1, correlated. And y is just x1 plus x2. And I start with missing completely at random settings. So missing completely at random. My data is just, I've just lost some data points at random. And so here, I can, maybe we don't need the enable iterative imputer anymore. Yes. Oh, we do. God. I've just imputed some data. Can you see the imputed data? Yeah, there's a line, right? If you squint a bit, there's a line. Where's that line? So the iterative imputer by default uses a linear model to impute one feature as a function of another. Actually, if we squint a lot, we probably can see two lines. You know, it's x1 imputed as a function of x0, x0 imputed as a function of x1. They're typically not exactly the same, right? So then, you know, we can build a pipeline on this. Here we build a pipeline combining the iterative imputer with the ridge. And we can, you know, compute the scores, and we get what? We get scores of 0.6, 0.7, all right, on the imputed data. We can do the same thing using a mean imputation. So mean imputation here is kind of brutal. Sorry, I'm going a bit fast. Do you want to type along, or is it fine to go on my screen? Okay, cool. So you know, we've done the imputation, mean imputation. So mean imputation is going to create, you know, those vertical, horizontal lines. So it's brutal, as I mentioned. It's a brutal distortion of the data, and we can apply a ridge on this, and we get 4 prediction score. We can do the same thing. So now we no longer need to enable his gradient boosting. We can do the same exact things. And here we're doing this. Here we're doing this on data that hasn't been imputed. Are we? Yes, we're doing this on data that hasn't been imputed. So I'll cover why later. The orders of my slide are suboptimal. But basically, his gradient boosting does not need imputation. And so we get scores that look better. I'll do a plot right now. Can we compare? Well, here, iterative imputer plus ridge works better than the others, and mean imputation plus ridge is the worst option. Okay, why? How many data points do I have? Maybe, you know, that's the first question we should ask ourselves. In samples, 500. So I have 500 data points. So 500 data points is kind of on the low end to fit a gradient boosted model. And here, my data generating mechanism is actually a linear model. So here, my ridge comes in really with the right kind of inductive bias. But for ridge to work, we need the data to be imputed in a way that recovers that linear generating mechanism, right? Because if we don't recover the linear generating mechanism, the ridge is no longer well posed. It no longer corresponds to the actual way the data was generated. Okay, let's try the same exact thing with 20,000 data points. Now it's going to take longer to run, especially with his gradient. But what are your guesses? Any guesses? Sorry? Gradient boosting is going to outperform. Oh, that was a good guess. Well, here it's a tie, right? It's a tie between gradient boosting and iterative imputation. What we can see is that really gradient boosting is completely caught up, okay? But here, you know, we're in an ideal setting. Here, we're in a setting where x1 and x2 are very correlated. It's a Gaussian, so they're basically linearly dependent, where the expectation of x1 is linearly dependent from the expectation of x2. And y is a linear function of x1 and x2. So basically, iterative imputer and ridge are fully well posed. The equations that they estimate are the actual equations of the data generating mechanism. That never happens in real life. Still. Oh, and we're missing completely at random. Okay, how about doing the same exact thing, but here I'm creating censored data. Okay, so My data is missing. Now, what I represent in gray is actually, not a lost data point. It's a data point with one of the two features missing, or maybe both. But so my data is missing more likely above a certain threshold. So it's missing not at random setting. And here I can run the iterative imputer again. So what do you notice? All right. There's something in the center. Yeah, there's something, actually, what you really need to look at is the color. And what you see is that there is something in the center. There's like light colors. Light colors mean high values of Y in the center. Because the thing is, so because we didn't model the censoring, we're no longer recovering well we're distorting the distribution. Basically, it's a distorted distribution. The missingness distorts the distribution. And as we're distorting the distribution, we're taking data points that should have been, but we can't notice, that should have been, far out, and we're moving them back in. Now, that's disastrous for what we want to do. Why? Back to the colors. Because it's breaking the link between X and Y. So not only have we not recovered properly the distribution of X, but I don't really care. We've broken the link between X and Y. Now that's probably going to take forever, but here I'm trying a bunch of things. So, Ridge with mean imputation, iterative imputation, his gradient boosting, and even iterative imputing in his gradient boosting. So what do we see? Well, it's actually, the differences are actually quite small. We see that Ridge no longer works. Ridge no longer works, even though the generative mechanism is linear. And the reason Ridge no longer works, even though the generative mechanism is linear, is because we have broken this linear link between X and Y, because now that they're censoring, we're always imputing below. And so we're breaking this link. So even though the data generative mechanism is linear, our imputation is breaking this link. And a gradient boosting actually can recover. And what we find is that iterative imputer or native handling of missing values of gradient boosting actually outperforms mean imputation. Okay, so what we have here is an illustration a bit about our theorem, is basically what the theorem tells us, and later results will show the same thing, is that the learner is actually compensating for missing values. The learner is compensating for weird patterns that are created in the data due to missing values. And so maybe, one intuition that I really, really, really want you to remember is that when we impute, we're creating patterns in the data. Those patterns may create distortion with regard to the original data. If your goal is to do inference on the data like there was no missing value, your goal is to minimize those distortions, and you're going to work a lot on this. If your goal is to predict with missing values, it's a different thing. What you want is something that can capture those patterns and predict from them. It's a different thing, right? Okie dokie. Let me switch back to the slides. All right, so we've seen all that. A few more theoretical results. Many intuitions are wrong in imputation. First of all, so typically when people discuss imputation, publish an imputation, without being explicit, they claim the idea of a good imputer is an imputer that captures the conditional expectancy of the missing values given the observed. Okay? That's typically what people want. So chaining the oracle conditional expectancy of the missing with the observed with the oracle predictor without missing value doesn't give an optimal predictor, doesn't give a consistent predictor for data with missing values. And the reason is that you're replacing distributions by expectations, and by doing this, you're forgetting all the higher order moments. So typically you're forgetting variance. And if you have a nonlinear function, the nonlinear function turns variance into bias. Okay, so once again, the intuition that if I get the perfect conditional expectation and I get the perfect regressor with full data, I get the perfect regressor with missing values is wrong. And then the question is, can you fix this? And we have some more complicated results that show that if you try if you get the perfect conditional expectation and you try to learn a prediction function that compensates for the missing values, for the bias that you have created, you're going to get discontinuities. So basically, you need a learner that can actually learn discontinuities. So your perfect conditional imputation doesn't really fully simplify the problem for the learner. And same thing, if you try to fix your prediction function, then you lead to discontinuous imputations. So basically, you end up having there are certain scenarios where you end up having discontinuities if you try to do sophisticated imputation. So what I'm trying to say here is we don't have a infinitely powerful theorem to tell you that no conditional imputation won't work in general. I'm just saying it's not a magic bullet. It will not magically solve the problem. Okay, so another point of view, and I already mentioned this in the notebooks, is to say, well, we're going to have architectures that model missing values, and one example is trees. And trees, once again, there are a bunch of if-then decisions. So you can special case the if-then decisions to special case for missing value. So this is what XGBoost like GBM or his gradient boosting do. And the recent versions of scikit-learn random forest do that too. So really, the tree is just doing if-thens. So it special cases the missing values. And so what we see is that if we do small simulations, this works really well in missing completely at random settings. It also works really well in missing not at random setting. And in missing not at random setting, it really makes sense. Missingness is actually signal. So modeling it is really good. Okay, so more recently, very recently, this is a preprint that hasn't been accepted yet. And we did with Marine Le Morvan, we did a fairly complete empirical study on real data set of imputation for prediction. And here we took we made the choice of studying only missing completely at random settings. Why do we study only missing completely at random settings? Because those are best case scenarios. We know the theory tells us, the experiments tell us that if the data is missing not at random, then imputation is going to struggle. So if we take missing completely at random setting, and we did empirical results to know, how important was missing value. And just to summarize the paper very briefly, what we find is that better imputation is useful, but you get really diminishing returns in the sense that you need to improve. I mean, the gains that you get in imputation transfer very little to the gains that you get in prediction. And once again, the problem is that the imputation can be much, much more costly than prediction. Things that surprised us, or things that are kind of new, is that missingness indicator is useful even in missing completely at random settings. And the way I understand this is it helps the predictor correcting for the missingness patterns that are created. And thing that surprised me is that in missing completely at random settings, having a good imputation plus the missingness indicator outperforms tree-based handling of missing values. Now, how much this carries over to real-life scenario, I do not know, because my experience of real-life scenario is that they're not missing at random. They're typically missing not at random. If your data is missing, there's a reason why it's missing. So my take-home message is imputation is useful, but comes in with diminishing returns, and I always need to use the missingness indicator. So typically, in terms of budget of time, I will not overdo it. I will not allocate crazy budgets of time in imputation. I will rather allocate budget of time in having a flexible learner that allows me to learn the imputation imperfections. Any questions on this part? Maybe I should say the tree methods are really good at all those missingness aspects, because not only can they model missing values natively, but also they can very well model the kind of irregularities that imputation creates. If you have smooth predictors, you probably need to work on your imputation better. So typically, if you have neural nets, unless they natively handle missing values. Okay, so my recipes for fitting numerical data. So you've guessed, I tend to use trees a lot. They cater for missing values. But if you don't want to use trees, you need to do preprocessing that makes the distributions more regular, and you might need to impute missing values, but that might be costly. There are better ways of doing things than iterative imputer, but they might also have convergence challenges, so they're not in scikit-learn. Okay, now I want to talk about something different, more exciting, and I don't need to start talking faster. I want to talk about all the other kind of columns than the numerical ones. And to me, by the way, this is the real problem. Numerical values is where statistics like to go because it's the math are well written, but the data typically has columns like this. So one way to solve them is to transform them. So once again, this is data messaging. It's tiring, and so I'll go back to something I already said. It's really important to separate fitting from transforming, because when you don't do this, you create leaks, but also because one of the big problems of industrial data science is that the data scientist does pandas and scikit-learn in his Jupyter notebooks, and then calls IT production and says it's ready, you do it, and then once they try to transfer this to production, it doesn't work. It's just in 101 story of data science in real life. And one of the problems is because they've done all the data munging in pandas script. You can't separate fitting from transforming. So given new data, what do? Okay, so once again, I can do things like categorical encoding using pandas, but if a new data comes in, what if there is, I sorted to get the new orders of the columns, what if there is a new category, a different one? So you know this, we don't do this, we use one-hot encoder rather than using a pandas get dummy, because it ensures all these things. So that's really, really important, and that's what Scrub provides for all kind of other transformations. So typically you have tables, dates. There, you can do interesting transformations to dates. You can turn the date into the times in seconds since the epoch. You can get out the day of the week, the month, things like this. All these things can be done by a Scrub datetime encoder. And so it can fit the data and transform the data, and has hyperparameters that can be tuned, hyperparameter optimization. Okay, so data messaging is about doing all kind of transformers, applying scikit-learn transformers or scrub transformers, or one-hot encoding, Gaussian, quantile transformer, the datetime encoder on the different columns in a pipeline. It's easy. But then we get, those columns that are really nasty, made of strings. So a few tricks that work well. The first one is target encoding. Target encoding is this very weird idea that you're going to replace a category by the expected outcome, the expected Y, given the category. Why is this interesting? Because you're basically injecting these categories in a number, so R, And you're injecting those categories in a way that is consistent with what you're trying to predict. So basically here we're putting the people who typically, the job descriptions who typically have higher salaries on one end, and the job descriptions who typically have higher salaries on the other end. Okay, so this, takes the problem with what I call dirty categories, so those open-ended strings, is that they're very high cardinality. And so here you take this very high cardinality thing that you can't really one-hot encode, and you throw it in a single line. Now, the few tricks is that typically you want the expectation, and the expectation is not the mean, and so typically you need to regularize it in a way or another to avoid overfitting. And one thing that we've done over the years is to model the strings rather than consider these things as categories. The reason is that typically there's more information in the string than just, a discrete information. And so one way to do this is to use classic topic modeling from NLP, where the idea is that you're going to do a counting of occurrences of words. And here we do counting of occurrences of substrings. And then you're going to build a count matrix. And then you're going to factorize your count matrix. This is, latent models. You're going to factorize your count matrix, and then you're going to get, topics and loadings. And so if you do this well, it's quite robust to things like convergence hyperparameters. We call this the gap encoder, stands for gamma Poisson. It's the matrix factorization that works well on this kind of data. The reason I like this is it gives you this kind of representation. So you have the strings. The strings are, we represent them as loadings on latent factors. Those loadings are positive and sparse. So you can see that each category can be seen as loading on a small number of latent topics, which are basically latent categories. We can even give feature names that are basically which words, it's completely heuristic as which words are frequent in there. And so basically this is a very interpretable representation of open-ended strings in the data. So it's done in the skrub gap encoder, and it comes with feature names, and people really want feature names. So it's, it's recovering categorical-like encoding from more open-ended strings, typically categories that have not been normalized. So the problem with the gap encoder is that it can be slow. So we have another approach that's based on hashing strings. So it uses min hash. So min hash is a probabilistic hashing method that's used, for instance, in large-scale databases. The reason it's used in large-scale databases is that it's hash collisions, or the probability of hash collisions is basically proportional to the Jacquard index. And so we use min hash on substrings. And so it's a randomized representation, so it's hard to interpret. But what you get, and we showed this in the paper, is that if you have all the strings that contain a given word have a representation that is lower, in the sense of each coordinate that is lower than the hashing of this word. So all the strings that contain supply are lower than the representation of supply. So for instance, here I've shown senior supply technician, and you can see that it's below in all directions the hashing of supply, the hashing of technician, and the hashing of senior. So it's very hard to interpret. It's very hard to get a picture in your brain. But if you go back to tree-based models are doing cuts on this space that we've created. It's a very abstract space, but they're doing cuts. And by doing cuts on this space, they're basically selecting for subsets. Okay? So the min hash encoder actually works extremely well with tree-based models. And it's extremely fast because it's based on randomized hashing. So it's stateless, you can apply it in parallel to many things. And finally, one question is, okay, those are strings. Maybe we should encode them with large language models. And so recently, Leo Genstein, and I can't see if he's in the room or not, did an empirical study and showed that large language models do bring benefits. So one question is, do they outperform things like TF-IDF representations? Do they outperform the min-hash encoder? And so the answer is yes. So we study, which model is best, and unfortunately, the bigger is better. And I say unfortunately because, we computer scientists love a lot of great things, big things, but these things incur real costs. The hospitals I work with just cannot use these things. It's a real problem, by the way. I really, really, really want to draw the attention to the cost of what we've been doing has been bubbling, and most of us are paid closely or not by the tech sector, which makes money out of this, and that's why the tech sector is very, very happy, but the non-tech sector is not happy at all. So because we were worried by the cost, we had a look at, what's the driving factors behind this performance benefit. And what we see first is that the performance in the kind of applications we have, so prediction on tabular data, correlates very well with the performance on what's known as the massive text embedding benchmark, which is a classic benchmark of text embedding with language models. But we also saw that this was only useful for columns that have what I call diverse entries. What I call a diverse entry is columns for which the number of unique n-grams per 1,000 rows grows quickly. So what I mean by this is the entries are very, very different from one another. So this is not, it's not related to the length of the entry. You can have very long entries that look very similar, but you can have short entries like names of artists on Spotify. Names of artists on Spotify, there's no repetition because basically people are trying to have a unique brand name. Okay, so typically one way of looking at this is looking at how many unique n-grams, character level n-grams you have in 1,000 rows. So really you can see that this is a fairly good predictor of the benefit of using a language model, including a large language model in a column. So what we don't have, but I'd like to have, is to, do experiments where all the models that don't have diverse entries are encoded with, like, all the columns that don't have diverse entries are encoded with min-hash, and all the columns that do have diverse entries are encoded with language models. That would be one way of being somewhat parsimonious with the resources. Okay, so to summarize a bit, those messy columns, if you want interpretable encoding, you can use the gap encoder. If you have trees, so the gap encoder is based on a stochastic solver of matrix factorization, so it may sometimes be slow to converge. Not too bad, but if you have trees, actually the best encoding is typically done with min-hash encoder, which is very, very fast and works well with trees. And if you have diverse entries, it might be useful to use some form of language models. Okay, so, back to what I presented. I've basically presented you, some kind of list of, well, if you have this, then you should do this. If you have this, then you should do this. It's tedious to do in practice. So Skrub comes in with a table vectorizer that basically applies those heuristics, the heuristics that I've described. And so it has, all kind of heuristics and cutoffs to encode the different columns in different ways. So it's very nice to use because, you just make a pipeline between the table, pipelining the table vectorizer with the learner that you prefer. And it can be used readily. So this is what's behind the tabular learner. Currently, we don't have the notion of diverse entry in it. We should add it. By the way, this paper isn't published. It's on arXiv, but Leo basically thought it wasn't cool enough and tried to do cooler stuff. So if you think it's cool, you need to tell him so that he actually submits it. He's around. Okay, so we all like hyperparameter optimization. So the table vectorizer comes in with a bunch of hyperparameters and should have more, maybe. And so maybe, that's a call to the community. Maybe, it'd be interesting to include this in hyper optimization strategies and benchmark. What we find is that those hyperparameters, depend on the downstream learner. If I know that I have trees, I can use a min-hash encoder. But if I have linear models, I really, really, really shouldn't use a min-hash encoder. It's going to give me disastrous representation. I could choose my imputation strategy as a function of what I have downstream. So these choices are implemented in Scrub tabular learner. And the reason why we have a function is that you can give it a learner. It basically wraps it with preprocessing. I'm also interested in improving the heuristics we have in Scrub Tabular Learner. So Scrub is a young package. It means we can still change things. Scikit-learn is an old package. Changing something is very, very hard. Scrub, we can change things. So if you all do good science that tells us how to do Scrub better, we'll improve it. Okay. So Scrub Tabular Learner is basically his gradient boosting with table vectorize. Okay, I want to talk a bit about more recent work. And basically, I'll talk about two things. I'll talk about like a neural network-ish a thing that we did recently, and I'll discuss also the comparison that they're in this paper. So you know what, okay, I've got two options. I can either go fast on the neural network-ish thing because it's somewhat off topic and it's not only about data preparation, and spend more details on the benchmark, which have taught us a lot, and leave enough time for many questions. Or I can go more in detail in the neural network-ish thing, and there will be less question. What do you want? Show of hands, more details of the neural network-ish things. Show of hands, questions. All right, I'll do a bit of both, but you want the neural network-ish thing. Okay, so going back to neural networks, the successes of neural network outside of academia have been from pre-trained models or very large data sets, but people don't have time, money, and data to fit very large networks in outside of academia. What people really do is they download a model and they use it because it's of reasonable cost. So the question is, how can we pre-train for data tables? And what's a prior for a bunch of numbers? What can you tell me about this table? Nothing, right? We can have priors, but how about now? Lots of things. Now, if I have a column and the column height has a 1,000, we know it's an outlier. The point I'm trying to make here is that it's really hard doesn't mean impossible, to devise priors if I just have numbers and if I don't know the meaning of those numbers. But if I know the meaning of the numbers, then I can come up with priors as a human being, but neural networks can do this. It's the same thing, if you take vision, if you take language, things carry over from one data set to another. So the challenge is to have more things carry over from one data set to another with neural networks. And so if I want to be a bit fancy, I'll say that the ChatGPT moment of tabular learning will come from contextualizing numbers with associated strings. If we really want to break through, this is what we need. So we have two challenges here. One is entity matchings. Different entities mean different things. This can be done by string level modeling. It's related to the language models on the entries that I've presented before. And the other one is schema matching, the fact that different columns mean different things in different data sets. And this, I'll show how we do this. We do this using a model of the local relational graph. And once we've done this, we can pre-train on large data sources and get benefits. So one thing that we do is that we transform tables to graphs. So here you can see a table and you can see its graph representation, and the idea being that each pair of a column actually corresponds to one edge. So I have cities, and so the entry, San Francisco, becomes a node in the graph, and then it's connected with different edges to the other columns. So it's connected to the value population via an edge that's labeled as population. So it's the column name. It's connected to the value state via an edge that's called state, okay? So those columns. So we didn't invent this. This is very classic in databases. It's one way of representing data across multiple tables. It's used in knowledge graph. So we're using this because it allows us to represent all kinds of different tables in the same data structure. So once we have this, then we use language model embeddings for all the strings, including the column names. And we use the representation that I've shown, and we use a graph transformer architecture. And I don't want to go into details because I'm running out of time and it's not the topic of the talk. But basically, once we have this, we can pre-train and we get a model that seems to work well. And I really think this is just the beginning, by the way. So this model is called CART, and we're excited about this. Okay, so I mean, why does it work? Once again, it's a tabular transformer in a sense, but what's important is that it models. So what I didn't say, by the way, is that we don't tokenize the strings. Sorry, we don't tokenize the numbers. The numbers are represented in the transformer by a specific way of representing the numbers in the transformer. And I think this is really important because I think that, you know, wherever we go, we need to model strings and numbers in a good way for both string and numbers. Okay, so what I want to spend time on is the empirical evaluation of this paper. So it got accepted, which tells you that CART was well performing, but we did a lot of work on the baselines, and I found this really, really interesting. So there are many, so you can look at the paper, but there are many, many teachings that I want to point out. First, that the combination of LLMs and trees, we've kind of seen it before, the combination of LLM and trees, tree-based models works really well because, you know, it's good for strings. LLMs are good for strings, tree-based models are good for the rest, and combining them works really well. So it's, you know, the first few models off the cart were this combination. Then CatBoost works really, really well. What we see is that Scrub Stable Vectorizer was extremely useful to basically adapt. So yes, I should stress the kind of data we're validating on is the kind of data I've been talking about. So it's data with columns of all kinds of different nature, strings, things like this. It's not purely numerical data, obviously. So the table vectorizer was really good in the sense that it could adapt this data to many different models. And interestingly, the logistic regression was the best performer. I forgot to say, we're looking at small sample settings. We're looking at up to 1,000 samples. So in a sense, it's not that surprising that later models work really well. Other teachings, this was interesting. I mean, we tried a bunch of, so there's TAP-PFN, which is a really interesting neural networks that works very well with tables of numbers. So we tried a, you know, bunch of different ways of adapting those tables that are more complex than just tables of numbers to TAP-PFN. And what seemed to work better was to use target encoding. And one last thing, bagging in general tends to benefit a lot neural networks. And neural networks here, we didn't have huge success with them, but what we found is that consistently bagging improved neural networks. So, you know, if you're interested in pre-processing for machine learning, this paper has actually a lot of learnings that are in the baselines and not only in the contribution. Jun, who is the lead author, did a lot of work on the baselines. Okay, so in the interest of time, I'm going to wrap up. So what we find is that basically rich representations and rich machine learning can partly automate data preparation. And really the reason is that part of data preparation has historically been matching the data to the models. So if we have models that are more flexible, we need less data matching. I think it's really important to explore the trade-offs between computational cost and statistical performance. It's something we never discuss, and CART, by the way, doesn't do well at all there. I think it's crucial. I think we need to have this discussion as a community. We shouldn't accept a paper that doesn't discuss this. And the reviewers gave us a hard time on CART about this, and they were right. And also, I think, you know, okay, so we are solving prediction. And that means we should worry about statistical thinking. Not thinking about what the missing values mean that we have disastrous interpretation. Interpreting non-causal models as causal models means we have problems, sampling biases. Okay, and finally, I'm super excited about Scrub. So for data preparation, the tabular vectorizer is super useful, but really the goal is to have a package that really facilitates machine learning on tables. We're going to pack more and more good defaults on the tabular learner, and we're super happy to hear from you, ideally with empirical evidence. And as you've seen, Skrub does much more. You've seen a bit of visualization with a table report, but it's going to work on data assembly much more. And I want to stress that Scrub is a community project. It's not only run by my lab, it's run by many labs. And we're hoping to have, try to reproduce what's being done in scikit-learn. Thank you very much.